Get your attention on me. Talk about Professor Caitlin Casey, who is visiting us from UT Austin today. It's their first seminar for the semester, in fact, I believe. So let's see if I get this right. You, at a very young age, finished your PhD from the University of Cambridge at 2010 before taking a Hubble Fellowship and then another prize fellowship I can't remember the name of, to UC Irvine. The Q, that's it. The Q Fellowship before starting her assistant professor job at UT Austin, where she now resides. So she works at all things dusty and luminous at high redshift, and she'll be telling us about some of those.
Yeah, great. Thanks, Casey. It's great to finally be here. This is my first trip to College Station, and I felt it was a little overdue that I come out here, because it's not that far. Yeah, so thanks for having me. I'm happy to start off your semester. And today I'm going to be talking about broadly dusty star-forming galaxies in the early universe. So these are some of the most rare luminous galaxies in the universe. They're also the most prodigiously star-forming galaxies that are out there. But just to give you like a notion of how rare they are, there are roughly 100 normal type Milky Way galaxies producing the same amount of stars as just one of these dusty star-forming galaxies, or DSFGs, which is an acronym that I'll be using. Today, though, so that's what I do broadly, is dusty star-forming galaxies. But today I want to talk about them in a pretty interesting context, which is the formation of galaxy clusters themselves. So because they are such a rare galaxy population, they can actually be used to try to constrain the assembly history of galaxy clusters in a way that normal galaxies cannot be used. So I'll be talking about that. This is all summarized in a paper, I should say, or like the idea of this method is summarized in a paper from last year. Can we
Do the light.
So yeah, there are these lights. This light that was on. Now can we? Yeah, perfect, perfect, great.
Enough light from outside.
Sunlight should be enough.
Yeah.
I think.
Actually, we can deal with that too.
Oh well, we don't need to
How do
make
I-
it totally.
No, we'll fall asleep.
Okay.
It's not my problem.
Awesome. So, and please interrupt with questions if I'm saying something. I would rather this be a conversation and a discussion than just a lecture. Cool. So just to put it in context in terms of the galaxy cluster science, I think it's an interesting question to ask, you know, how do these galaxy clusters themselves assemble? So we have this beautiful like theoretical picture from simulations that shows the collapse of large-scale structure from initial density fluctuations, and you get, you know, a rather complex structure at around 2.5, and then at redshift 0 you end up with these really massive galaxy clusters that are the most massive gravitationally bound structures in the universe. And they're of course of cosmological interest. This whole process of large-scale structure collapse tells us about cosmology itself. But also from the galaxy evolution point of view, it gives us very interesting insight on, if we're able to study this, how environment changes the evolution of galaxies. So we want to understand how a galaxy that's living in an overdensity like this is different from a galaxy that lives in void or in underdensity. And observationally, we have a few constraints. So there's been a great wealth of work that's been done on galaxy clusters themselves, from the X-ray to radio SZ measurements. But you know, pushing that out to higher and higher redshifts is difficult. And you know, it hits a wall somewhere around redshift 1.5, depending on, you know, what you think is the highest redshift cluster that we found. And then observationally, we don't have a very good handle on things until we get all the way, you know, to the CMB, and that's our observational signature of, okay, here are these density fluctuations. And there's a big gap in between that we're just starting to now fill in with studies of turbo clusters. And so the theoretical framework links the two observational pieces, and what we want to try to do is fill in the middle observationally. And just to kind of enlighten where I'm going with this and show you my conclusions now, what I'm going to try to argue over the course of this seminar is that collections of very rare galaxies, in particular these dusty star-forming galaxies and quasars together, can teach us about the assembly history of clusters in this pre-virialized state, when the structure still extends over a very large volume and is overdense but has not yet collapsed into the clusters we see today. Okay, and to kind of just frame in a cartoon version of this conclusion, what I'm going to say is, okay, we know observationally what kind of galaxies live in galaxy clusters. So we can count up the massive constituents. Say there are 50 massive galaxies in galaxy clusters at redshift 1. So above a certain mass threshold, there will be n number of galaxies. And we assume, those are the typical end products of rare quasars and rare dusty star-forming galaxies. And so if we assume all of those massive galaxies at one point or another between redshift, say 6 and 2, went through this very luminous, short-lived phase when it was extremely bright and was forming many stars, then we can ask, what's the likelihood that we see 10 of them at once over that interval of time? And so it's a really simple problem, just given a time scale of how short-lived these systems are. How likely is it that randomly we see 10 at once if in the end we get 50 massive galaxies? So that's the question we're answering now with observations, and through constraining that time scale, we want to address, well, are clusters themselves more likely to assemble in stochastic bursts where these bursts indicate episodes of rapid star formation that take place across the scale of the protocluster? Or is it a much more gradual process that's randomized?
So actually,
Yeah.
I mean, there must be some influence or prediction from SAMs on this.
Yeah,
I mean,
yeah,
They're,
so
they're
this
probably
is-
all over the place, but.
Yeah, well, no, they aren't. But they're in the SAMs. So this is one of the things we want to ask in more detail. The problem, so if you want to answer this question with simulations, you run up against the issue that for very large clusters, you do need SAMs, you need semi-analytic models. But then it's very difficult to know how to paint on,
Like the physics right.
the physics right to predict whether or not you get a dusty star-forming galaxy. So that's the main limitation in testing it with SAMs. But it's certainly something that we'd like to do. So I've just mostly been attacking this from the observational point of view. Yeah, that's a great comment. Okay, so first I just want to get folks all on the same page by giving a few details on DSFGs in general, if you don't know much about dusty star-forming galaxies. And then I'll discuss in more detail how we're using them as beacons of protoclusters. So the first bit of the talk will just be a review of this population. So I said at the beginning of the talk that dusty star-forming galaxies are very rare by number, but have very high star formation rates. And they're particularly rare by number in the local universe. So this is split up into luminosity class. This is the cosmic star formation rate density as a function of redshift, so Lilly-Maddow plot. And you can see the most luminous infrared galaxies, or ULIRGs, are not even on the plot, right? They're not contributing substantially at all to cosmic star formation. But at redshift 2, they're over 1,000-fold more common. There are many more galaxies that have very high star formation rates and are very luminous in the infrared. And so they're certainly important to overall cosmic star formation in the early universe. So this is another version of the Lilly-Maddow plot, but split now into components of luminosity, coming out at long wavelengths and luminosity coming out at short wavelengths in the rest frame UV. So this is all of the rest frame UV measurements. You know, HST pushing to very high redshifts has been successful in trying to constrain cosmic star formation. But we've been pretty lousy at you know, having complete surveys out to high redshift just from long wavelengths. So we're complete to about redshift of 2, and you can see the important role of long wavelength surveys. Now, the long wavelengths is just reprocessing the rest frame UV emission from young stars, massive stars, and through dust reprocessing. So that emission is being absorbed and re-radiated at long wavelengths. So dust has a really influential role, but then we're incomplete beyond redshift of 2, and then we don't even have decent surveys that probe the early universe in terms of dust constraints. So, yeah.
What do you mean by infrared complete?
Infrared complete is that we have actually a good handle on the completeness of surveys. Just, we have a good constraint of the luminosity function, basically. And here we have sources, but we don't know how incomplete they are, just because getting the redshifts is...
Okay, but so by the luminosity function you mean infrared luminosity?
The infrared luminosity function.
Okay,
yeah.
so you're not just talking about just the alerts and alerts.
No, yeah, exactly. So I should say that here I'm taking out the IR contribution from galaxies that are selected at optical.
Right, in other words, the blue points are just the raw observed.
Just raw observed, yeah. So normally we see this right up here, but that's because it's folding in that corrected value. That's like a factor of 5 normally. So this kind of shows that in a bit more detail. So this is a plot of the fraction of star formation that is obscured versus total star formation for a galaxy. So this is a compilation of both local and high redshift samples, just showing you as the SFR cranks up, you see that most of that emission is actually coming out at long wavelengths. So even in the Lyman Break galaxy regime, you're seeing 80 to 90% obscuration, and in the dusty star forming galaxy regime, you're seeing 98, 99% obscuration. There's a better version of this plot, which Kate Whitaker and I are working on publishing soon this year. She breaks it down by stellar mass. And what's really interesting is that the fraction of obscure star formation rate seems to be a strong function of stellar mass, but it also doesn't evolve over, out to redshift 2.5 or so. So expect to see that soon on arXiv. Okay, and then the last point that I mentioned earlier too is that the population is really rare. So this is a plot of the so-called galaxy main sequence, the close relationship between stellar mass and star formation rate. And I like to show it as a contour plot to just emphasize the fact that sources that sit on the main sequence at low stellar masses are much more common and not necessarily directly related to sources at the high end of the mass function or high end of the star formation rates function. And dusty star forming galaxy selection is basically a flat selection in star formation rate. And L star falls somewhere right here. Okay. Now, one point I can make physically about these dusty star-forming galaxies, there's been a great deal of work over the past, 2 decades on this population, 2 decades now, not a decade, that looks at their kinematics in detail. So, asking what actually triggers their extreme star formation. And we see in many cases, they're predominantly merger-driven, major merger-driven, and they're short-lived. So we measure the gas, molecular gas mass, we know their star formation rate, we can compute a depletion timescale. And so this is just a histogram of the depletion timescale for about 70 of these DSFGs from Bothwell et al. 2013. Some detailed kinematics show really beautiful examples of mergers. But I should also point out that there are notable exceptions to this picture. GN20, which is one of the brightest submillimeter, most well-studied submillimeter galaxies out there, it shows really nice rotation, consistent with a disk. And there are other examples as well that are consistent with sources, with not being driven through major mergers. So this is still an open topic, but certainly at the high luminosity end, most are merger driven. It's also really hard to get redshifts for the population overall. This is traditionally the bottleneck in our field. And we go from these submillimeter maps, often constrained heavily by the spatial resolution, and we just try to figure out exactly which source corresponds to the submillimeter emission at other wavelengths, follow those up spectroscopically, and what we get out on the other end is some population that is biased in relatively unknown ways. And I should just point out that this is still a struggle today, even though we have this beautiful new instrument called ALMA, and we can get spectroscopic confirmations for submillimeter sources through ALMA. It's very time intensive for individual sources to do this, so we can't do this for populations yet. So optical near-infrared spectroscopic confirmations are still the most efficient way for studying this population. We've had substantial improvements, though, in the past 5 years getting larger spectroscopic samples. So here's a redshift distribution from our work on Keck, which shows the number of DSFGs that have spectroscopic redshifts. Of course, the tail at high redshift just is much more difficult to get those, not that we think they don't exist. And then here's the kind of growing number of sources that have molecular gas observations. So this is a subset of these sources. And you can see that this maxed out really around 200 just a few years ago. It hasn't really grown substantially since. So we're working with small numbers overall. Why have give us more time with ALMA? Yeah, no. So it's an issue that CO observations with ALMA take an hour or two per source, and so we're really just incrementally growing at this point.
It's the kind of thing where you've already gone through all the ones that are bright enough in the optical near-infrared study, and
Yeah.
now you're
Okay. So we need an order of magnitude jump here somewhere along the line. Okay, but there is hope that we can become more efficient at spectroscopically confirming these at very high redshifts. I showed you the dire picture that we're not doing a great job beyond redshift 2.5, but there are really neat examples like HFLS3 at redshift 6.3, this extremely luminous source, star formation rate 1,000 solar masses per year. The stellar mass is harder to measure just because there's almost nothing coming out. This is an HST image with a foreground galaxy removed, and there's basically nothing at the point of the submillimeter emission. And what we need to do is become more efficient at finding sources like these. We know they exist, and they can place interesting constraints on dust formation in the early universe, but we really need to improve our technique in finding these. Okay, so one of the things I'll briefly advertise, which we're trying to do, is to improve in this regime, specifically at very high redshifts greater than 5, by using longer wavelengths in the millimeter. So instead of doing our typical submillimeter surveys at 850 microns or 1 millimeter, by surveying the sky at 2 millimeters, we're particularly sensitive to higher redshift sources beyond redshift 3 and filtering out foreground things below redshift 3. And so this is an ALMA cycle 5 proposal we'll put in, again, with the Cosmos team. We proposed it last cycle as well. And we'll be pushing for a 2 millimeter dust continuum map with ALMA to find these sources at higher redshift and be more complete in our accounting of them.
But you'll still have trouble getting the actual redshifts.
Yeah, but we'll have the spatial resolution to follow them up in a more efficient way. Yeah, absolutely. Okay, so that's dusty star-forming galaxies in a nutshell. So I'm going to now use that knowledge that we've built up of the population to talk about them in protocluster environments. Okay, so here's kind of the illustration, my nice little cartoon of a galaxy cluster in formation with dusty star-forming galaxies. And what I want to really emphasize here is I think we're just now getting to the point of being able to recover DSFG populations spectroscopically to a point that we are revealing more associations. Like so spectroscopic completeness, it's really hard, but we're getting to a point where we're starting to see structures come out beyond a redshift of 2. Okay, so before I talk about protoclusters, I want to first just talk about clusters briefly. Everyone defines this in a slightly different way, but I would say, a cluster is really defined from the presence of a hot intercluster medium, and that intercluster medium will emit via thermal Bremsstrahlung radiation at X-ray, and it can also absorb CMB photons via the SC effect. So this is, the gas that's just in the intercluster medium has been heated through, the kinetic infall of all of the material, and these observational signatures are defining aspects of galaxy clusters in many ways. And so here's an illustration of the SC effect thermally, and also kinetically. You can try to resolve motion outside of the Hubble flow for clusters themselves. Okay, so then protoclusters you can easily define as structures that just don't have that signature. So they don't have a hot intercluster medium yet. So they're still extended and diffuse structures, even though they are over densities in the universe. So observationally, how protoclusters are often revealed, and there's been loads of work done in this arena over the past few decades, is narrowband imaging, particularly looking in the vicinity of very rare galaxies, like radiolab quasars. So it's thought that because radiolab quasars are such, massive evolved systems, that they must have, they must live in the most enhanced regions in the universe. And so indeed, narrowband imaging surveys have revealed that many of them, like some high fraction, 75% or so, do have overdensities of, for example, Lyman alpha emitters. So if you image the field with a narrow band, then you pick up that emission from either Lyman alpha or H alpha, and you see the overdensity pop out. On the simulation side of protocluster work, one could ask, okay, well, if we don't want to see that hot intercluster medium, then what do structures that become massive galaxy clusters at redshift 0, what do they look like at this epoch at redshift 2? And it shouldn't be surprising that before the intercluster medium heats up, these structures are extended over very large physical scales. And the physical scale over which they're extended maps to their redshift 0 halo mass. So as you march up in halo mass, you actually see a very, very large structure as the progenitor. And this can be 10 to 20 megaparsecs co-moving across. This is seen in a variety of simulations. Here I'm just pulling one from Jose Oñorbe's work that was more testing the initial conditions of simulations, but you can also use it to say what is the co-moving volume of halos between redshift of 2 and redshift of 0, and what is that change? And if you have a cluster at redshift of 0, something that has a characteristic radius of 2 megaparsecs, and back that up, then you do expect something to live within a 20 megaparsec box. And so what does that translate to observationally? We're now looking at half-degree to degree scales on the sky, which, just for scale, I have the moon here as a nice illustrative example. So this gets to be a much more difficult observational problem now that we're looking at very large scales on the sky. And we have to be able to map these structures over that scale. Okay, so when we're observationally measuring this quantity, we want to pull out some indicator of the overdensity. So I'm going to use delta gal here, which is basically what you measure some typical density of galaxies in the field, and then say, okay, in this region, how overdense am I? So it's the observed number of galaxies minus the expected over the expected. So this is really limited by your ability to measure the field luminosity function well. So you need to know the luminosity function of your galaxies pretty well. And your survey, whatever it is, should be spectroscopically complete. If it's not, then you won't be able to measure delta gal very well, even if there is an overdensity there. And if you work all of this out, given typical luminosity functions of Lyman-Barrett galaxies at redshift 2, and constraints on what we can actually observe with the surveys that we have, you expect to measure a delta gal of 3 to 8, so a factor of a few. And this is, if you detect 100 or so sources or more in your overdensity. So this is really, in many ways, it's an observational limit, but that's what is also predicted from simulations. So given the issues with normal galaxies, I want to say, so the usefulness of rare galaxies should be almost obvious that, okay, well, you're needing to compare to a background, and rare galaxies are very rare by definition. So if you do see an overdensity of those rare galaxies, then you can much more easily distinguish an overdensity. So just as a cartoon of what I'm talking about here, say you have a filament at redshift 2.5 that, again, stretches half a degree on the sky. It has these galaxies that sit inside of it, but obviously, observationally, we don't see this. We see several galaxies in the field, and the background level is quite high, so it's very hard to distinguish the filament if you don't have a very complete survey. But say you have a rare galaxy in the middle of this, similar to our radiolab quasars, then you might get the idea you should search in the vicinity of that rare galaxy for other constituents that sit in its vicinity. And you might find, the handful that sit right around here. But if you have, a collection of these rare systems that map out the filament, then you might be much more efficient at finding the underlying structure. Okay, so now I'll describe some of the really interesting protocluster associations that do have an overdensity of these rare systems. So the SSA22 protocluster, it's a really well-known structure at redshift 3.09. It's debatable exactly how many dusty star-forming galaxies it contains, depending on your luminosity cut. But it has something like 5 to 8 very, very bright DSFGs, and they're also associated with Lyman alpha blobs. And what's interesting about this structure, since it's been around for a while, The extended field of view has really been mapped out well in terms of its Lyman alpha emission. And it's just now, really starting to fill in at sub-millimeter wavelengths as well. There's also the HDF structure. So there is an overdensity in Goods North at redshift 1.99 and redshift 2, but it just takes up the entire field. So this is all of Goods North. And the rare sources sitting in this structure are the red and the pink sources, and then the blue sources are just normal galaxies sitting in the structure. It's a little less significant, but it really has an interesting overdensity of these rare sources. Just to follow up with the SSA-22, this is some of the sub-millimeter follow-up that's been done with ALMA from Umehata et al. In 2015, and there's been more work recently just mapping in that structure. And then the HDF source, the HDF overdensity. What's interesting about it is it really has only marginal significance in normal galaxies, so it's only 2.5 sigma from the very large, very complete spectroscopic samples in HDF. But it also contains some really well-studied DSFGs, a pair of mergers that sit very close to one another, a massive radio galaxy. So here's one of the pair of mergers, massive radio galaxy, and then this source, which is a relic FR2 galaxy. So it actually has extended X-ray emission that has this double-lobed feature, which is very interesting and rare in and of itself.
Does it extend into the Goods North field? I mean, do you see the overdensity extend into the larger survey?
So I haven't mapped that, investigated that beyond the initial work.
I didn't know
So-
the sub-millimeter survey status of Goods North was, it's as deep as it is not.
Yeah, so it's deeper now.
Okay.
It's definitely deeper now. I don't think everything of interest has a good spec-C though. It's really only that central portion.
There's a lot of Herschel data there too.
Yeah, there is. So, this is all stuff that should, but so what's interesting is this structure, when it was initially found, was kind of dismissed as, probably not that massive, given that the overdensity of normal galaxies was so low. And so now I think that we found more of these, it would be interesting to go back to this one and look at it in more detail.
Agreed.
Yeah. Okay, so now I'm going to address the issue, possibly an elephant in the room, that we don't know that DSFG overdensities, like these rare galaxies, are actually telling us the truth. Maybe a very high overdensity in DSFGs just is random. It's sampling Poisson, it's limited by Poisson statistics. And the true mass overdensity, maybe that's traced much better by the normal galaxies. So this is, constraining the galaxy bias is what we want to do here. How do we take a measured galaxy overdensity and map it back to the mass overdensity? And this has been, a debate. Like I said, the HDF structure wasn't really accepted as a massive overdensity. And so this has been something that's been looked at in the simulations. Which population really traces the dark matter structure well? So in simulations, there has been work that looks at this in detail from large semi-analytic models, but again, you have to accept that with a little bit of caution in that in most simulations, you dramatically underestimate the number of dusty star-forming galaxies, period. It's a very difficult population to reproduce. But nevertheless, in those simulations, it seems as if DSFGs are probably not good tracers of the underlying dark matter structure, and they're really limited by Poisson noise. Okay, but again, I think this is something that really needs to be dug into more, in particular, given the limitations of the simulation to reproduce the population overall.
when you say simulations have trouble doing this, do you
Yeah.
mean like semi-analytic models, which
Yeah.
are kind of like simulations?
Yeah, so
or
you
do
need
mean,
the
like, actual,
semi-analytic models because otherwise you don't have enough volume to probe the
Okay, so
structure.
basically it's like, okay, so the semi-analytic models.
Yeah, that's the problem. I mean, like we can do, you know, the full hydro simulations, but they don't have
Yeah.
these structures, so
Okay.
yeah, that's the limitation. Okay, two more structures sit in Cosmos, one of which I know is known very well here by the ZForge team at Redshift 2.1, and then right behind it, there's another structure at Redshift 2.5, which we just stumbled on serendipitously through a Redshift survey of SMGs. So here's the ZForge protocluster kind of centered here, but it extends over a wide area if you actually look for SMGs in the structure. There's also a possibly related protocluster to the background structure revealed through Lyman alpha emitters in the HETDEX pilot project. So this is just a snapshot of these two Cosmos structures that sit on top of one another. Again, the Redshift 2.5 structure we just found more or less serendipitously, and indeed, like the scales here are, you know, this is 10 arc minutes, so this is really a large visible scale. And then looking at the Redshift 2.1 structure found by ZForge, the center has remarkably good spectroscopic follow-up from ZFire, but we were looking in Chaoling Hong's paper last year at the kind of extended structure, particularly several submillimeter galaxies that happen to also sit at the same redshifts. The 2.5 structure gets even more interesting if you look at the this interesting work from KG Lee on IGM tomography. So he's using background galaxies as probes of hydrogen in the intergalactic medium, looking at the Lyman alpha forest in a statistical sense. So these aren't bright quasars, and so you can't really look at an individual spectrum and say you know what's along the line of sight, but you can piece together a map of the intergalactic medium, and this little red dot in the corner here actually corresponds to the extended structure that we found. He followed it up in more detail, and indeed here's the Redshift 2.47 structure seen in absorption, which is pretty cool. And then there's this other kind of wing of it going down to the Redshift 2.4. And it gets even more wild. If I roughly map like where the dusty star-forming galaxies sit in redshift space, they more or less sit here. Now a lot of them are off the edge of the IGM tomography mapping, but there are also two way out here at redshift 2.55 and a bit. And that happens to be the same redshift where there's been this recent detection of X-ray emissions surrounding many red and massive galaxies from Wang et al. 2016. And Wang et al. Here suggests that this is indeed the highest redshift cluster detection to date. I think it's rather interesting that we have these neighboring redshifts that all seem to link together in what could be a massive super protocluster. A lot of observational follow-up is needed to actually string these together and see if we think the whole thing will collapse. We can look at observational evidence of like what's going on in the protoclusters. For example, looking at morphology where we have them from candles. The middle of both structures seem to conveniently sit in the candles portion of Cosmos. And there seems to be an enhancement of interactions from just the morphologies in protocluster members. So there's one other interesting structure that I think is worth mentioning that also has an overdensity of DSFGs, and that's the spiderweb protocluster. So the spiderweb galaxy itself is very interesting and even shows evidence of diffuse molecular gas over 100 to 150 kiloparsec scales right at the center of what is probably a massive protocluster. But it still needs wider field follow-up the way the other structures have been followed up. So overall, I would say there are 5 of these protoclusters that have strong evidence that they have an overabundance of these very rare dusty starbursts, in addition to the normal galaxy population that's just probed by this delta gal. Okay, so if we take these 5 structures overall and try to understand their selection and the volume that we've actually probed by deep surveys, and try to map that back into a volume density estimate for massive protoclusters, and compare that to the redshift 0 cluster mass function, we can ask, like, how common are they? So Andrew Blaine, did this back of the envelope calculation in 2004, given DSFG-rich structures, and actually came up with the idea that, they seem to be too common compared to the cluster mass function to actually be massive protoclusters themselves. So they must be probing much lower masses. Okay, but we redid this measurement based on the fact that some of those included in the Blaine calculation were not actually real protoclusters, and we get something that's more realistic. Now, how do we get the x-axis value here, the cluster mass estimate at redshift 0 for these? We do our best job in using abundance matching to estimate the total halo mass in the structure, and then forward that, fast forward that to redshift 0 to see what the cluster mass will be. So it's highly uncertain, but it at least agrees with the cluster mass function. But there's tension here too, because simulations, the simulations result that shows SMG-rich structures, DSFG-rich structures are very rare, has the point much lower. So most protoclusters should not have an overabundance of DSFGs. Okay, I actually mentioned this, that we already see an increased interaction fraction in protoclusters compared to the field, looking at just morphologies. One thing we're trying to do now is get into, is trying to measure and constrain the gas mass in protocluster members, not just the dusty star-forming galaxies, but all of the protocluster members. And we can do this through submillimeter observations. Here we're trying to do it with stacking of single dish submillimeter data. That's intrinsically limited, and so we're going to ALMA, and so we have a cycle 4 program that follows up individual sources with ALMA. So to answer this question, whether or not massive protoclusters have just enhanced gas feeding, that we'll see an overall elevation of the gas fraction in all galaxies, or if there's just enhanced triggering of merging, which only preferentially enhances DSFGs. Okay, this is breaking down the luminosity function of galaxies in protoclusters as opposed to the field. So the field is the black line plus the orange line here. And then here we have protoclusters that seem to indicate that we have a really, top-heavy, predominant population of very high star formation galaxies. And what we want to answer now is fill in this gap, which is incomplete. You can't really see it, but there's dashed here for incomplete. And what we want to ask, we want to differentiate between these two models. Is the enhancement only at the high luminosity end, or is it overall seen in all galaxies? Okay, the last little thing I want to mention here has to do with timescales. So how can we use the timescale of DSFGs to constrain that assembly history? So asking the question specifically, how likely is it for us to see 2, 3, 5, 10 DSFGs in any given protocluster at a given time? So if we look at the population of DSFGs overall, we accept that they have an average gas depletion timescale of 100 megayears. But there is some suggestion, again, that some of them might be long-lived on gigayear timescales. But for the short term, let's just assume they all have a 100 megayear timescale. And then we can ask the question that I posed in the beginning, just this very simple thought experiment that at redshift 1 you have n massive galaxies, which at one point between some high redshift range, redshift 6 and 2, they were dusty star-forming galaxies. And so what is the probability that we see them all at once? Or what is the probability that we see n rare galaxies as a function of their timescale? So if the timescale is very short, it's very unlikely that we'll see them all go off together. But if it's long, then that's a much more likely scenario. So for long timescales, we see actually 70% probability that we'll see 5 in the structure at once. Whereas if they're only living for 100 megayears, which data tell us they are, then the probability of just seeing 5 at once is only 4%. And we're seeing 10 to 12 of these at once. So the probability that they're just randomly going off at the same time is very low.
Sorry, you said, I'm reading this,
Yeah.
which is, so if you have data that show it, is it just like a gas consumption time?
So this is, okay, the data that show this are of the population in general, not DSFGs that actually live in the structure. So that's what we're doing now, is that, okay, for the population at large, that tells us that this is really unlikely, but what about the DSFGs that live in the
Right, so
cluster?
we're actually thinking like,
So that's what we're looking at.
either they have more gas or they're gonna get more gas.
Yeah, right. Maybe they're just a different type of DSFG than in the field. So that's the question is, okay, if it's really unlikely and they are short-lived, then perhaps they're triggered together. These events are correlated, these short-lived events. And you could imagine a scenario where a very large filament extended over 10 megaparsecs collapse laterally and triggers SMGs all along the filament. Okay, but alternately, you can imagine if you have an overabundance of these rare galaxies, maybe that's telling us the opposite, that they are not short-lived, that they're long-lived. And there's just some process of increased gas fueling in overdense environments that can sustain that high star formation. Okay, so we don't know the answer to this, but we're trying to assemble the best data set possible that actually looks at DSFGs in protocluster environments. So this is a very messy table, but this column right here shows you the derived depletion timescale for DSFGs living in protoclusters. So this is the data we have so far, and we're gathering more data now, but so far it seems like most of them are indeed short-lived. This is just a sneak peek of even more data for the 2.5 structure. We have this complex seen in CO1 to 0 with the VLA that my grad student Jackie Champagne is working on writing up. So in conclusion, I hopefully have convinced you at least a little bit that these collections of rare galaxies can be useful for trying to start to understand the assembly history of galaxy clusters themselves, and can teach us about the extended structure that probably falls into a galaxy cluster since redshift 2, but it is a very good probe of large-scale structure beyond redshift 2. And if we get more of these valuable gas measurements, then I think they will also be very useful for putting a constraint on whether or not you get these triggering effects of filamentary collapse, triggering star formation on very large scales. But also, very important points, protoclusters are huge and require observational campaigns on degree scales. And a remarkable access can really be interesting for probing protocluster assembly history. And meanwhile, we're getting much better at observing the population of DSFGs overall. And so all of these together will hopefully be a really interesting, provide a really interesting landscape over the next 5 to 10 years in looking at large-scale structure environments. Thank you.
More questions?
I'll start. So it sounds like you're coming down the side that it's some sort of, protocluster-wide star formation triggering event.
Right, which sounds
Short
pretty
time.
wild.
It does. It was like trying to work out like what is the, somehow everything always happens on like the dynamical time of the
Yeah.
crossing time, right? So
Right.
that's got to be really long.
Yeah,
Especially
right,
if you're talking
really
about
long.
megaparsecs in size, because
Mhm.
you can't be moving more than a few hundred kilometers.
Like, this is kind of ridiculous to suggest, yeah.
Yeah, we finished my question.
Yeah.
So
Yeah.
so I guess I would come down the side of, maybe it's hinting at longer gas consumption. time
Yeah,
scales. But I
yeah,
guess
so
what
that's
you're trying to
totally,
test.
that's a valid thing to suggest. And, so that's where getting to these actual
Yeah, right.
constraints on, okay, any DSFG that lives in a protocluster, can we do a better job at constraining the gas depletion timescale? So, I mean, like here we have,
Can I ask,
one
if
that
you're going
lives.
from CO, what is this, 2?
Yeah,
Or
okay,
what is
yeah,
it?
so that's totally a caveat.
Right.
Yeah, that we're going from a high JCO transition, you have to translate that to a low JCO.
These are high J.
These are high J.
Okay.
Translate that to a low J, translate low JCO to,
Right, so you can imagine there's a lot
Molecular
of
height.
lower
Yeah,
excitation
so
gas running around.
these values kind of fold in a lot of that uncertainty.
Okay.
And we do see sources, like this one is very long-lived, for example. But also, this is not the end of the story. Like, you could measure a short depletion timescale and still have gas replenish.
Absolutely, I mean, it's kind of expected if
Right.
all these nodes and the things, gas is
Yeah,
just going to keep
so I
going
think
down.
it's also interesting to look at it from the point of view of looking at the less massive galaxies, the lower star formation rate galaxies, and pose the question from this point of view, and if we take holistically, the luminosity function of all of the galaxies together, do we see that in these enhanced environments, is there overall a boost in the star formation rate that's caused by the overabundance of gas?
So it'd be like normalize everything at fixed elements.
Right, is everything just bumped up? Or is it just the high end that's bumped up?
Yeah.
Which you would think is more consistent with mergers versus everything being bumped up, which is a better signature of maybe just everything is more gas enhanced.
So why don't you have the data right now to pull this in?
For,
You just
oh,
need more
where
steps.
do these points come from?
No.
No.
Which of these two curves is correct? How are you going to figure that out?
Oh, so what we want to do what we want to do is fill in, just actually attempt to be more spectroscopically complete
So
in the
that's-
normal
Okay.
galaxy population of these protoclusters. Because it's basically an arbitrary subset of galaxies that have been spectroscopically confirmed in the structure. So it's not at all complete. So it's not really, we don't expect to find many more in this scenario, but here we would expect to, the protocluster members to go through the roof.
More questions for you?
So Jessica, your
Yeah.
collaborator last semester, and I've kind of connected his arguments to what's going on here.
Yeah.
And we kind of talked about this a little bit
Yeah.
earlier this morning. So he was arguing that like the gas was obtained by sort of mergers of larger numbers of smaller gas galaxies? Is that is that his argument as it pertains to you?
Yeah, exactly. Like that you can sustain high star formation rates for longer periods of time using, small galaxies.
And what is small, actually? obviously.
Well, it doesn't matter because they're all gas rich,
Yeah.
right? There's anything that falls in is going to be
Yeah, I
gas
mean,
rich,
anything
right?
that falls in.
Well, as
is
opposed to
gonna
like,
be unusual.
massive, more larger scale murders, major murders.
Oh, I see what you're saying.
Whatever.
I see.
Yeah, I mean, so like 1 to 10, you know.
Right. Like a
Or,
scale.
or
So he's talking, his are 1 to 10
ish, yeah.
ish.
Yeah.
And, like
Which is
1 to
pretty
1
much what I would consider like accretion at this point. I mean,
Yeah.
it's
Yeah,
just
yeah,
like
that's
gas
basically
rich
just,
blobs
you
are
know,
just coming in.
how are you gonna distinguish a minor murder from just random?
Just right.
So I should mention that there
That's
is
your-
also one constraint on the other end too, in that we cannot have high star formation rates for a giga-year and end up with 10 to the 12 solar masses, you know, across the board. Because we have like measured stellar mass functions of clusters at low redshift, and that's just not gonna work out. So that's a constraint on the other end to say, no, we have to cut this off after, you know, 500 megayears, like that's the absolute limit. So it would be interesting to try to piece together, you know, star formation histories for DSFGs and protoclusters and map that to the redshift 1 and below cluster stellar mass function.
Well, I'm sure. Maybe it's that we kept up. I mean, if you added all the stellar mass in something like
Yeah.
a coma-sized cluster,
Yeah.
you get a cluster medium, everything, your cluster light. I just remember like the cluster light's like half the stellar mass of the galaxy.
Oh, okay, yeah, so that would be,
So maybe there's wiggle room in there.
I mean, that's not something that I've really explored in detail, that's kind of on the to-do list, so that would be
Yeah.
interesting. Yeah, I don't know. Factor 2.
Right.
But yeah,
I'm trying to remember if Dashiga was talking about this or not, like taking fire-like simulations of, you know, zoom in on these
Yeah.
high-density regions and redo the memory process. Is that stuff?
well, yeah, but they're, I mean, the boxes aren't big enough.
They're still not big
really.
enough? Okay.
They're still not big
So
enough. You really have to go just all the way to
So
the
you get
biggest
over into topological
sands.
size thing, yeah, okay.
Yeah.
So you're kind of stuck.
Yeah, unfortunately, so gotta improve our computation.
Then this will inform the.
Yeah,
viewers when they
yeah.
get there.
So, anyway.
Any more questions? All right, well, thank you again.